So now this is the phase diagram. As I always tell you that when you look at any diagram, don't get confused, don't get afraid that, oh, this is complicated and so on. We will take it step by step. We will always explain each item separately. So don't worry at all. If you look at the vertical axis and the horizontal axis, it is a standard phase diagram. Vertical axis is temperature in degrees Celsius and horizontal axis is the composition in weight percent of carbon, right? So this is it. And if you see, we have 100% iron here, right? But here we don't have carbon, we have iron carbide, iron carbide. This iron carbide is also called cementite. Iron carbide is also called cementite. Other things you see, you have the alpha phase here, you have the gamma phase, which is austenite here, you have the delta phase, which is delta ferrite here, you have the liquid phase. But this here or here or here is the cementite or the iron carbide. See, chemically it is iron carbide, but on this phase diagram of steel, it is also known as cementite. So alpha is ferrite, gamma is austenite, delta is delta ferrite, and iron carbide Fe3C is cementite. So we have four solid phases. The liquid phase is there, liquid L, and delta, gamma, alpha, and ferrite cementite, right? So there are four solid phases. So this is the iron carbide diagram. Uh, it is just that you see at very high temperatures of 1600 Celsius or above, the whole steel is completely liquid. When you start to solidify it, then you have the liquidous line and this and that and so forth. Before I go on, I will try to explain why we not call it iron carbon. Why do we call it iron carbide? You see, this is 0% carbon, 1%, 2%, 3%, 4%, 5%, 6% carbon. If iron was completely soluble in carbon and carbon was completely soluble in iron, we will go to 100% carbon, right, on the right hand side. But that is not there. What happens is, when we try to add carbon, right, until 6%, it dissolves. When we get to 6.67% of carbon, when we add 6.67% of carbon, then everything, all the iron and all the carbon, start a chemical reaction and all of them convert to iron carbide. So we don't have any iron left now. So going further after that is no use, right? So on the left we have 0% carbon, on the right we have 6.67% carbon. This is the maximum amount of carbon. After that there is no solution of carbon in iron, but all the iron and all the carbon combine together to form the new material cementite or iron carbide, and there is no steel left after that, right? Therefore, we end the diagram on 6.67% carbon, and therefore we say it is a carbon iron carbide, iron carbide diagram. Iron on one side, iron carbide on the other side, not carbon only. Okay, so this is the reason. Now, if you look at the diagram, any place, I mean, you are here, you hit the liquidus line, it will start to convert into gamma. So there will be liquid plus gamma. You keep on going down, right? Keep on going down. Uh, Once you hit this temperature, then there will be some cementite form. We will see some cementite form if you go below. So now, if you remember your eutectic point. What was the eutectic point? Can you remind me? Think back from the previous lectures. Normally, when you have liquid metal and it is binary like iron and carbon here or lead and tin, and you slowly cool it, then liquid first becomes liquid plus solid and then it becomes solid. What happens at eutectic? All the liquid turns into solid, right? And usually it turns into two solids. So is there any point like that here? All the liquid changes into two solids. Yes, you are very right. It is this point here. The liquid is here, You see, if the liquid is here, it will go to liquid plus gamma. If liquid is here, it will go to liquid plus cementite. But if you are here, exactly here, then liquid, 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 and suddenly when you hit this point, it changes into austenite and cementite. Right? Gamma phase and iron carbide phase. So liquid changes into two solids, austenite and cementite at this point. This point is 4.3% carbon and the temperature is 1148 Celsius, right? So at this composition and this temperature, 4.3% carbon with iron and 1148 Celsius. At this point, the eutectic reaction takes place. All the liquid changes into austenite gamma and cementite iron carbide. So this is the a special point where the liquid suddenly changes into solids rather than liquid into liquid plus solid and then. Is there any other similar point, not exactly the same, but similar point where one material suddenly changes into two materials? Where one material suddenly changes into two materials. Can you see? Yes, you are again correct. This is the point. You see, above it is austenite, right? Above it, so this is a solid phase. This is not liquid now, but it is a single solid phase, right? Single solid phase. When you hit this point, it suddenly changes into two solid phases. So gamma austenite here suddenly changes into alpha, which is ferrite, and cementite or iron carbide. So one solid phase suddenly changes into two solid phases. The composition is 0.8% carbon. The temperature is 723 Celsius. So this is another special point, that if the composition is 0.8% carbon, which of course means 99.2% iron, 0.8% carbon, and at 723 Celsius, then all the solid gamma or all the solid austenite suddenly changes into the two solids, ferrite and cementite, right? Alpha or iron carbide. Now, you see, above this are these things, but below this temperature, this is all anywhere here, anywhere below the 723 Celsius, it is alpha ferrite and cementite. So whether you are at 600 or 500 or 400 or at room temperature of 20-25 Celsius, it is always. So this is what normal steel will be. Normal steel at room temperature will be alpha ferrite and cementite. This will be a combination of these two, and it, right, remember, it will not be iron and carbon. Iron and carbon are not there, you see, because iron makes this iron carbide. So this is called an intermetallic sometimes, that you see it forms a new substance. Normally, if you remember in lead tin or copper nickel, then there, right, in the end you have whatever we have, the alpha phase or the beta phase, but in the alpha phase or the beta phase there is either copper or either nickel, there is either lead or tin. Here we have iron, of course, iron, this is alpha is iron, but we don't have carbon. Carbon exists in steel as iron carbide, cementite, wherever you see, here also, there is liquid, there is delta iron, there is gamma iron, there is alpha iron, but there is no carbon. Carbon exists as iron carbide everywhere. So this is it, right? So we are just trying to explain to you, and you should not worry. What you will see is that, you see, normally steel has only a small amount of carbon. Steel is only a small amount of carbon. This is 0.02%. There is alpha here. You see this inside here is alpha. Inside here is alpha. This whole thing is gamma. So in between here is alpha plus gamma, right? This is alpha. On your extreme left, this is small portion is alpha, and it finishes at only 0.02% carbon. If you have more than 0.02% carbon, you don't have plain alpha anymore, right? Plain alpha exists only here. And at higher temperature, you have gamma, and this, the area between anywhere will be alpha plus gamma, right? Alpha plus gamma. Here in this very small portion at a very high temperature is 1400 plus, you have delta, very small. And then here inside, that was liquid, that is the liquid region, and this is the delta region. So this is the liquid plus delta, isn't it? Now this will be liquid, and if you go here, it will be gamma, right? This delta, don't get confused, delta is only here, this is all gamma. So this is liquid line, this is gamma line. Therefore, in between you have liquid plus gamma, liquid plus austenite, right? This is the liquid line, this is the austenite line. Okay. Here is the cementite line. Here, right? After this, there is cementite. So this is liquid. When you touch it, the liquid is liquid plus cementite. If you go below, right? Cementite is here. So if you go below, then on the right hand side you have cementite, right? On the right hand side, you see this is cementite line. This 6.67% is cementite. So here you have cementite, there you have gamma. Therefore, in between you have gamma plus cementite, right? Here you have cementite, here you have alpha in the corner. So in between you have alpha plus cementite. So this is how it is, right? Always, whenever you are in this region, right hand side is liquid, left hand side is austenite. So in between you have liquid plus gamma. In this region, right hand side is cementite, left hand side is gamma. So you have gamma plus cementite or austenite plus cementite. So this is how it will be everywhere, right? So this is the iron carbide phase diagram, which means that it is the phase diagram for plain carbon steel, right? Plain carbon steel. When we have added only carbon to the steel, we have not added any other alloying materials like manganese and so on. So if you want to give it a name, it is a binary non-isomorphous, right? It is a binary non-isomorphous. Now this point is the eutectic point. Liquid changes to two solids. This is something new. A solid changes to two solids. So they said that this is similar but different. So what name should we give? This is eutectic. This is eutectoid, like eutectic, right? So it is a very nice name, that if this name is eutectic, liquid to two solids, then a similar reaction of one material into two materials directly, but solid to two solids, let us call it eutectoid. So now we can call it binary eutectoid phase diagram, yeah, if you like. Binary because iron and carbon are the only two materials that we are combining, so it is binary. But it is not isomorphous, it is not simple eutectic, it is eutectoid. So we don't call it that, but if you like, you can say that the steel phase diagram is a binary eutectoid phase diagram, right? So almost everything, because this is just another example of a phase diagram, and you already did a eutectic, binary eutectic, so therefore this is not too much different. It is just that a eutectoid point is also added. But the main complication, or what is good for materials engineers, is the phases of iron, the three solid phases of iron, alpha, gamma and delta. So because of them we have many phases here, and once we add carbon, then carbon does not stay as a separate carbon, it makes a compound with carbon called iron carbide or cementite. Therefore we have four solid phases here, alpha, delta and gamma for iron, and cementite, four solid and liquid. So there are a total of 5 phases including the liquid phase here. The temperatures, if you remember, there are very important temperatures. 723 Celsius. 723 Celsius is the eutectoid temperature. 1148 Celsius is the eutectic temperature. So these two are important. 723 is the eutectoid temperature because here the eutectoid reaction happens. And 1148 is the eutectic temperature because here the eutectic reaction takes place. Otherwise, you know that room temperature we have alpha, 700 plus we become gamma, 1400 plus we become delta, right, and so on. So this is the iron carbide phase diagram.